So now we'll start with another test of the controllability, what we say the Lyapunov test. So consider now the LTI systems. Here on the left hand side it is the continuous time, and here it's the discrete time where we are using the same variable t. Uh, whenever we whenever it is implicitly clear that the in which domain are we talking about the test. Okay, so it says that assume that A is a stability matrix. So it is so note this point because we will going to use this argument. Assume that the matrix A is a stable. The LTI system, that is the pair AB, is controllable if and only if there is a unique positive definite solution W to the following Lyapunov equation. So this Lyapunov equation is in the continuous time domain. Excuse me, continuous time domain, and this one is in the discrete time. Okay, here we have used that the Lyapunov equation with respect when we are talking of the Lyapunov equation in the context of testing the controllability. Hmm? Because if you recall that the Lyapunov equation we have studied while stating the stability result, that Lyapunov equation is slightly different from this equation. Okay, though both of them are the Lyapunov equation because they can be represented in either way. Moreover, the unique solution to this to this Lyapunov equation is given by this W, and this is the reachability Gramian computed over the limit t1 minus t0 tending to infinity. Again, this is in the continuous time, and this is in the discrete time. Okay. So we shall see the proof. So here the first statement is basically that the system is controllable, and the second statement that W is a solution to this equation which is unique and positive definite. Okay, so we'll show the proof for the continuous time. For the discrete time systems it can be proved in a similar way. So first of all we'll show that the second implies one, that if W is a solution to that Lyapunov equation implies that the system is controllable. Okay, and we use the eigenvector test to prove this implication. So just to recall for the eigenvector test that associated to lambda there is an eigenvector of A transpose X which satisfy this equation and does not satisfy that B transpose X is equal to 0. Okay, this was the eigenvector test. So we start with the assumption that the Lyapunov equation holds, which is also this implication, and X is a non-zero vector or eigenvector of A transpose associated with the eigenvalue of lambda, that is it satisfies A transpose X is equal to lambda times X. Okay, then we can write, if you see the left hand side of the Lyapunov equation, we can use that which is also a matrix, and it is an assumption already in this implication that W satisfies this equation, that equation. Okay, so I can write that matrix in the quadratic forms, which is X transpose this weight matrix into X, which is nothing but equal to minus X complex conjugate transpose B transpose into X. Okay, again using the property of the norm, I can replace this whole quantity by the square norm of B transpose X. Okay, so we'll play with this quadratic form. So see it from at the left hand side that the first term we would have is X star AWX. Okay, let's write this just for the clarity, that we would have X star AWX. Okay, now this term I can write as A transpose X star transpose and its transpose. Only this term, because it would become x star into A, which is nothing but this one. Okay, so by just taking the transpose, I have replaced this part. The rest of the part Wx remains as it is. Plus, we would have x star W A transpose into X is equal to, now using this equation, we have A transpose X is equal to lambda times X. So I have replaced this part and this part by lambda times X using this equation. So here we would have lambda star X star, because lambda is an eigenvalue, and taking the and it could be a complex number also. Okay, lambda star X star into Wx plus lambda into X star Wx. Since X is lambda is a scalar, I could write this lambda star plus lambda into this quadratic form, and this is nothing but twice the real part of that eigenvalue. Okay, if the eigenvalue is already real, then it stays as it is, otherwise the imaginary part would go away. Okay, so finally I would have twice into real part of that eigenvalue into that quadratic form. So since W is positive definite, this expression, which is given in the equation number 11, must be strictly negative. Why? Here we have X star into X. W is already positive definite. So this part would definitely be positive. Now here we are taking only the real part of the eigenvalue of lambda, and since there is an assumption that A is a stability matrix, so the eigenvalue must definitely be on the left hand side. So this term would definitely be negative. Okay, if it would be negative, then it will never be equal to 0, because on the right hand side we have minus of norm B transpose into X. So if let's write this just for the clarity, that if I see this equation, on the left hand side we have just shown that it must be strictly negative. So it must be some negative C, where C is a positive number. Okay, this I can write as B transpose X square. Okay, meaning to say that B transpose X would never be equal to 0. It would be equal to 0 if and only if this is equal to 0, which is not. Right? So we have just shown that there is an eigenvector of X. There is an eigenvector X of A transpose, for which this B transpose X not equal to 0 is satisfied. Okay, which implies that the system is controllable, because with that eigenvector test we have the if and only if condition for the controllability. Okay, now for the other way implication that the system is controllable implies that W is a solution of the Lyapunov equation, being the unique and positive definite. So we have assumed that the AB is controllable. So this previously studied Lyapunov equation is this one. The Lyapunov. So this previously studied is the Lyapunov equation we have studied while discussing the stability results in terms of Lyapunov. So that equation is basically given by this one. So this equation, if I see the equivalence between this equation and the Lyapunov equation we have introduced in this result, this is just a parameterized form in terms of A and B matrices. So if I replace this A bar here by A transpose and this Q matrix by B transpose, I would obtain the Lyapunov equation which we are talking about in this result. Okay, so here since A is a stability matrix, A bar would also be stable, because taking the transpose would not change its eigenvalues. Okay, the allocation of the eigenvalues would remain the same, and if A is a stable matrix, then A bar would definitely be. And therefore we can use or reuse the proof of the Lyapunov stability theorem, which says that given a matrix, a positive definite Q matrix, if there exists a solution of solution matrix W being unique and positive definite satisfying this equation, then the eigenvalues of this A bar would strictly be onto the left hand side. Okay, so we can use that result to prove uh, that W would be a unique solution to this Lyapunov equation what we are speaking in the context of controllability. But now there is a slight difference here, that here Q is basically given by B into B transpose. Okay, so now B could be any matrix. Let's suppose if my B is a vector, just for an example, which says that we have a single input, and if I compute this Q, which is 1 0 0 and B transpose 1 0 0, it would be 1 0 0, right? And the off diagonal, all the off diagonal element are also 0. So here it is not necessary that Q is also a positive definite. Q here could be positive semi definite also, right? So we just need to take care of that thing, that here because Q is now having a specific form of B into B transpose, it is not necessarily to be positive definite. But it turns out that the controllability of the pair AB, which is already an assumption, that the controllability of the pair AB suffices to establish that W is positive definite even if Q is not. So this is important here. So let's see how. So indeed, given any arbitrary vector x which is not equal to 0, and I write this quadratic form x transpose Wx. Okay, now W, I have used the same W which has been given in the result. So we need to prove that W is unique and positive definite and satisfy this Lyapunov equation, in spite of knowing that Q is not necessarily a positive definite matrix. Okay, so we have this one. Now notice here that here we are computing the integral from 0 to infinity. Okay, now if I come, and it is nothing but a norm square. It is nothing but a norm square which inside with the integrand, which meaning to say that it is always be positive. So if I am computing the integral over 0 to infinity, and if I compute that integral from 0 to 1, I would definitely have this value would be greater than if I compute that integral over 0 to 1, because I know that the integrand is a positive quantity. Either it would be equal or would be greater whenever I compute this integral over 0 to infinity. And this is nothing but your reachability Gramian. X transpose WR is from 0 to 1 into X. And being the controllability, it says that the reachability Gramian must be positive definite. So I can have that this greater than or equal to 0, because this result is already known to us, that the controllability Gramian should definitely be positive definite, and it is already an assumption that the AB is controllable, which implies that this condition would definitely hold. If this holds, then it means that X transpose WX is positive definite. Okay, so we have just shown that W, which we have used as this one, which is nothing but the solution of the Lyapunov equation, is positive definite. Now the second one is the uniqueness. For the uniqueness, we could use the previously established result, where the idea behind showing the uniqueness is we could use two matrices. For the same Q, we can define two matrices, let's say W and W bar. Now the rest is to show that W and W bar are not different, but they both are equal, which shows or which establishes the uniqueness. So that part we won't be discussing again, but you can refer to the Lyapunov stability theorem part. Okay. So the result of this theorem in fact allow us to add a sixth equivalent statement to the Lyapunov stability theorem. So now we have just updated that Lyapunov stability result, that the system, this homogeneous CLTI, is asymptotically stable. The system is exponentially stable. So the first 5 statements, in fact, we have already shown the equivalence in the stability week, that all the eigenvalues have strictly negative real parts. For a given Q, P is a positive definite unique solution to this Lyapunov equation. So this Lyapunov equation we meant by the previously studied Lyapunov equation. And the fifth statement, that this matrix is negative definite. Okay. Now we have added this sixth statement, which also includes the controllability. So all these 6 statements in fact establishes both the results, stability plus controllability. That for every matrix B for which the pair AB is controllable, there exists a unique solution P to this Lyapunov equation in the context of the controllability. So that's why we have named these two Lyapunov equations differently. The first one, which is a standard one in the context of Lyapunov stability, the second one in the context of the controllability. Okay, it's just a representation, otherwise both of them remains the same. Moreover, P is symmetric, positive definite, and equals to this one. Here we have just replaced Q by BB transpose. Okay. So now the controllability tests is finished. This is just a summary of all the controllability tests we have studied. That the following statements are equivalent. The n-dimensional pair AB is controllable, which is equivalent to saying that the square matrix WC, which we have defined as the Gramian, which can take either this form or this form. If you notice that here we have used the T and T minus tau. This part you can prove it quite straightforwardly. So this is, we have defined as the Gramian matrix test. The Gramian matrix test we have also studied in the context of linear time varying systems. The third statement says that the n cross k times n controllability matrix, where k is the dimension of the control input. This matrix has rank n, or say that this is a full row rank. This is again a matrix S. So all these 5 results are in fact for the LTI case. Matrix test, we have the non-singularity of the Gramian for the linear time varying systems, but the matrix test, where we have explicitly computed the matrices, was a weaker result for the linear time varying case. But for the LTI system, it is a strong result. That again we have the if and only if condition for the non-singularity or the full row rank of this controllability matrix. 4, you can also say the eigenvector test or the matrix test, because both of them are related. That the matrix, this A minus lambda I, for all the eigenvalues of the matrix A, B has full row rank at every eigenvalue of A, which we have said that it is a PBH test, Popov-Belvich and Hottis test. Equivalent to that, we had additional condition that there is no eigenvector of A transpose in the kernel of B transpose. The fifth, if in addition all eigenvalues of A have negative real part, then the unique solution of this equation, which is the Lyapunov equation in terms of the controllability test, is positive definite and can be expressed as this part. So this finishes the controllability, all tests related to the controllability. Now we have some additional results which establishes the invariance and the decompositions of the controllability, because so far what we had seen that if this rank condition is satisfied, that the system is controllable. Now we also need to answer that if the rank condition is not satisfied, then under what circumstances we can still say that our system is controllable.